Please.
Yeah, speaking of not being very healthy, it probably looks as if I was in a brawl over the weekend, but actually I have some surgery on my nose a couple of weeks ago, and just last night I stood up underneath a tree branch too suddenly without looking at it. But I'm feeling pretty good. So I'm going to talk not so much about what I've been working on most of the time in quantum information, but some new ideas, many of which I don't really understand. So I would look for interruptions and objections and clarifications from the audience, or if any of you understand any of this stuff better. But it seems like important stuff to think about. So this is a general outline. I'm going to speak about how one, we imagine ourselves to be living in a very complicated and interesting universe. How do you define this complexity? Is there natural scientific reasons why we can understand from physics why it should spontaneously increase and make the world as interesting as it is? And then the fact that, especially in cosmology, in order to think about things like this, you have to worry about the observer bias. The fact that if the world was simple, there'd be nobody to complain about its simplicity or to enjoy its simplicity. And there's a variety of ideas related to that, including the question of apocalypses. What's the likelihood of the universe ending in the next second? Well, most of us think it isn't very likely to end in the next second because it hasn't so far, but actually that's not a sound reason for believing that it won't end in the next second. So this is connected with the old problem or the idea of Boltzmann brains and black hole firewalls. I'll talk about that a little bit. There are some things I really don't understand, which I'd like to, such as the Sleeping Beauty problem, which is close relative of the absent-minded driver problem. And then I'm going to talk toward the end about how we can think in non-anthropocentric ways about post-selection, about entropic principles. So let's start. Oh, I can do it with this. So everybody knows the manifestation of Occam's razor, that if a scientific theory is supposed to be explaining something, then the phenomenon that you actually get ought to be typical of what the theory says you should get. And this notion was captured very well by a cartoon by Sidney Harris, who does a lot of science cartoons. And I was tempted to reproduce it here, but he's got a pretty fierce policy about reproducing his cartoons without permission. So I will just, and actually the picture part of the cartoon is something that I could just have substituted a picture taken upstairs of a bunch of people standing around in front of a blackboard, because that's what it is, a bunch of scientists in front of a blackboard. And one of them is saying, if we run our picture of the universe backwards several billion years, we get something resembling Donald Duck. There must be something wrong here. So the problem is that the things like this are actually coming up in current cosmology. I became aware of that just within the last year or so. So it's fun to think about those things, especially as a newcomer to the field. But before we talk about cosmology, let's talk about something I've been thinking about for much longer time, for decades. Of course, there's a lot of different kinds of complexity, but the kind of complexity that we think of when we say that the world is in a complicated state, how can we formalize that mathematically? So I don't want to talk about, what is the laser button on this thing? Oh, that one, yeah. Life, or the ability to metabolize and reproduce and things like that. Closer to the idea that I want to think about is randomness or order, the two opposite things, or free energy. These are kind of thermodynamic potentials, or things that can be expressed in terms of information theory. Or correlation, mutual information. For example, there are mutual information between the pages of a book, or especially between the book and other copies of the book. And there's mutual information between this slide and my thumb, because that's how I made that thing. But then the thing I would like to argue is that it's the right way to formalize complexity is something called logical depth, which can be defined in terms of universal computation. But informally, it means that an object has internal evidence of a long and eventful history. And then there's other kinds of, these things I think, are getting close to the idea we want. This is a kind of complexity such as this Mandelbrot set, where we have a very complicated hierarchical self-similar structure. I don't think that's what I want to talk about. And then finally, we have an important idea of computational universality, such as a universal Turing machine, or this is a glider in the game of life, which is also closely related to what I want to talk about here in terms of complexity. And the point of talking about this, which is pretty old hat for me, and maybe for some of you who have been to some of my talks before, is that I want to tie it into the question of post-selection, of observer bias and what to do about it. So, as I said, you cannot identify complexity with just the thermodynamic potential or with either extremes of maximum order or maximum disorder or even any intermediate amount of order. And to see that, it's useful to consider two bacteriological situations here. We have a bottle of sterile nutrient solution, and then we have a bottle with a trillion bacteria in it. And if these are typical bacteria like E. coli, you don't need to put in here very much, just a few different nutrients. And this will spontaneously turn into that very quickly if you give it a seed bacterium. But if you don't, you might have to wait for a very long time. But nevertheless, the free energy of this is higher than that. So that this transition from the bacteria to the nutrient flask is prohibited by the second law. And this one is allowed, therefore, by the second law. But there's some other kind of law that prevents it from happening quickly. And indeed, you might say if you just put even one little bacterium in here, the complexity doesn't increase very much. So this complexity is not an extensive quantity. So rather than think about bacteria, let's take my favorite one-dimensional reversible cellular automaton. So I'm having time go this way. And it's something that produces structures of growing apparent complexity from simple initial conditions. So this is an initial condition that's periodic, but with a little defect there at the edge. And the consequence of this little defect, which actually happens both in the past and future, if I went back in that direction, you would also get this similar thing, is a kind of growing wake, like the wake behind a boat, but deterministic. Pattern that's all determined by what information was there, which is not very much. It's periodic except for one little defect. Well, here's the rule. It's a deterministic one-dimensional Ising model, but to make it non-trivial, it needs its interaction with the second neighbor as well as the first. Yes?
I guess the information you also need the time step, right? It's not just the initial information.
It's determined by two consecutive time slices. It's a second-order rule. It's in that way. It's similar to Newtonian mechanics. So in other words, you can determine the history of a mechanical system by giving the positions at two consecutive times, or by giving the position and velocity at one time.
Sure, but what I'm saying is that you were saying that at any time step, it doesn't have a lot of information because Well, it started with something so simple.
Yes.
But what I'm claiming is that, well, what I'm saying is that that's not really true because the time step itself.
Oh, you have to say how many time steps.
Right.
Exactly, and I'm glad you asked that question, but I'm sorry I didn't understand it because it's an important consideration that we're going to come to later. It's very important. So you have to say how long you've run.
Right.
Okay, so this is the rule. The past is different from the future if exactly 2 of the 4 neighbors at the present time are on and 2 of them are off. So here's what it does. And if getting on to your question, if you take a piece of it, a good-sized piece of it at this time, and you say, well, I don't know what the earlier evolution is, but where could this have come from? Well, you could run its evolution backward, but you don't have complete information because you don't know what to put in the rest of the system here. But you could try various things, and almost anything that you would put here would generate a kind of messy situation if you ran it backward in time. But if I put exactly all this stuff here, it would magically go back to being an extremely simple situation. So you might say that this configuration, even though it's partial configuration up here, contains strong evidence for the initial condition that it came from, and also for how long the evolution went from that initial condition, and indeed for what happened to the other parts of the evolution. However, if I take a little tiny piece of this weight, like that, well, you can see it could come from something that's entirely blank, except for this very simple periodic repeating pattern. So that doesn't have evidence for its true history or of any kind of non-trivial history because it's too small. So the approach I'm going to use for defining complexity is similar to the old idea of the monkey possibly typing out the works of Shakespeare. Of course, it's very hard to find a typewriter anymore, so the monkey would use a computer. And in order to make it easy for the monkey, we just give the computer 2 keys, 0 and 1. And it's a computer that behaves like a lot of computers, that it can lock up its keyboard and refuse to accept any input for a while, or maybe forever, depending on what you type into it. And this is an idea that I heard from Gregory Chaitin. I think he invented it, or maybe this is my translation of what he was trying to tell me back in 1975. But this means that you can think of all possible computations as a big binary tree, infinite binary tree, and we go down one of these branches if the monkey types a 0, and if it types a 1, we go down this branch. And then depending on this, it may immediately ask for another digit, say, and if I give it a 0, it will think for a while. That's what I've got, this resistor symbol, and then eventually ask for another digit and so on. And it may go on asking for infinitely many digits, or it may terminate with producing some number like the 2 to the 10th, which is relatively easy to compute from a small description. Or it's most typically it'll do what a computer will usually do, it'll run for a while, then it'll give you a syntax error. Or it can produce the number 2, or it can go on forever. Of course, it'll have a node in which it just simulates itself, because universal computers all have that property. It also can do Shakespeare, and it does it rather more efficiently than just an ordinary typewriter because of all the redundancy in Shakespeare. And it can compute the winner of the ideal chess game in the infrared spectrum of toluene and things like that. So if you want to think in a kind of mystical way, you could think of this input-output graph of a universal computer as the microcosm, not of everything that exists in the world, but everything that could exist in the world, or that you could understand through deductive reasoning or numerical simulation. Now, you might say, you can use this monkey tree to define a universal probability measure, which is the probability that a given output would be generated by by a terminating branch on this tree. That is the total probability. Of course, if you run this tree in parallel like this, a lot of the branches will be still thinking, and some of them will go on thinking forever, and because of the unsolvability of the halting problem, you will not be able to know whether a given branch terminates or not. So this universal probability distribution is not, the normalization constant for it is uncomputable, and it's known as Chaitin's omega. It's the total probability of halting of this computer. So it's not very useful, but it's for practical calculations, but it's an important idea to think about. So approaching the same thing from a slightly different direction, by Occam's razor principle, we would like to imagine that any phenomenon ought to be explained by the most concise economical hypothesis that explains it. And if you computerize Occam's razor with this monkey computer, the alternative programs the monkey could give it, alternative inputs, which are just binary strings, are here. The computation is what it does, and the output is, if it halts, this is what it produces. So we take all the different ways of producing a given output, and we favor the most concise description, that is the shortest input that generates it. Or if you wanted to think in a little more canonical way about it, you would say, let's take all the descriptions and weight them by exponential of their length and add them together and take the logarithm of that. And you get a number it's only different by an additive constant. So this gives rise to the theory of algorithmic information, or Kolmogorov complexity. But that's not what I want to talk about right now. I want to say that if you believe that this is the most plausible hypothesis, and that this one is, 32 times less plausible because it's 5 bits longer, then you also ought to believe that the computation by which this generates this is the plausible explanation of the origin of this object. The plausible amount of computational work required to create the object. And that's what I call the logical depth of the object. So in order to make this notion, yes?
What if you have two smallest programs? What if you have two smallest programs?
They would, the fact that if you combine all the programs, you get, and take if you take the algorithmic probability, which is the total probability of producing that output, take the logarithm of that, you can show that it differs by at most an additive constant from the length of the shortest program.
Sure, but you're going into logical depth, and I'm asking if you have two programs that are shortest for that input, but one does a lot more computation than the other. Say.
Oh, okay. No, I'll explain. I would say then in that case, if there are short programs that waste a lot of time, I don't care about them very much. But it's just that if all the short programs take a lot of time, then then the thing is deep. Keep asking questions like that. That's what I need. Oh, so to make this more stable, we use a 2-parameters definition. So you say that some object has depth D at confidence with confidence level S or significance level S. If every program to compute it in time less than D is compressible, that is, it's self-computable from a shorter program. That, in informal terms, this means that every hypothesis for producing the thing quickly is ad hoc in the sense that it could be generated by a simpler hypothesis that would take longer to generate the object in question. So we can go, I wanted to go through this a little quickly, unless there's a lot of questions about that. You can formalize this definition and make it stable in a reasonable way. And when you do, yes?
What is the role of D?
Yes, in this definition, depth D.
D represents the time. It has logical depth. D means that it probably requires time more than D computational steps to make it from a plausible description. And that says that if all programs that compute the string x can be computed, wait, all programs such. Oh, I think I left something out there. That's awful. I see. All programs, thank you. Yes, all programs that compute the string x in time less than d. Oh, I'm going to hurt myself again. I just kind of do that too much. Anyway, all programs that Okay, so that's the idea. Thank you. So anything that computes it faster than that could itself have been computed without a limitation on how long the computation took from something shorter and therefore more plausible. This turns out, there's another way of defining it. You could just say the string gets all but, it gets less than 2 to the minus s of its total probability from programs that run faster than d steps. And those two definitions are almost equivalent. And this one gives slightly nicer slow growth law. Okay, just getting back now to the less mathematically rigorous forms of talking about this thing. A trivially ordered sequence like all ones is shallow because it can be computed rapidly from a short description. A random sequence, such as the typical one made by coin tossing, is also shallow because it's its own most concise description. A typical random sequence generated by coin tossing cannot be significantly compressed because there are not enough short descriptions to go around. And so therefore, it typically can be generated quickly from a description of near minimal size. And that's the difference between depth and algorithmic information, or Kolmogorov complexity, which is the size of the minimal program. These things measure two different properties. This measures randomness, and depth measures the plausible amount of computation or dynamical steps to have produced something from an incompressible description, or near incompressible. Okay, let's go back to this. Of course, it's very hard to prove. It's an uncomputable property. The Kolmogorov complexity is itself uncomputable. Omega is uncomputable. Depth is, you can prove something deep by trying all of the fast ways to produce it and finding out that none of them works. But you can't prove that it's shallow. Because something that looks random might be pseudo-random with a very long time required to produce it from a small description, and you have not studied it for long enough to understand that. Or to take a biological example, there are some places in the world where the role of males in connection with pregnancy is not understood. And so in the worldview in those places, pregnancy is something that sometimes happens to women. But now we have another explanation for that, which is not at all obvious, perhaps to first thought. I mean, a lot of young kids are a little surprised about it when they hear about it. And yet, we now consider that a more plausible explanation, because it explains the data a little better. Well, anyway, so starting it back at this picture here, we would say, well, presumably this is the story of how this thing can be produced is there are not a lot of other programs that sneakily produce it much faster, or so let's imagine that this program is the main competing candidate. And so as you run this thing for a while, its depth will increase because it will have strong evidence for that computation. And we're getting back to your question. For quite a while, that will be the most plausible way to have this thing produced. However, if you let it run for a really long time, comparable to the exponential, of course this thing is a finite automaton. It has only whatever the width of this thing is, 2 to the n possible states. So eventually it has to repeat. And so if you run it for a time comparable to its Poincare recurrence time, the typical time slice will become shallow again. And the reason is,
Excuse me,
yeah,
I don't know the translation of the word shallow.
shallow is not deep. So deep is like going from here down to here, and shallow is like this. It's like if you step into a puddle outside, you get your feet wet, whereas if you step into the ocean, you drown. Yes. Yes. Okay. So the where do we go here? Yes. So so what I'm saying is here, if you let it run for a very long time, this slice, the minimal program for generating this slice is not something that runs for the entire time that you simulated it. Because to name that time, if it's longer than 2 to the n, to name exactly that time takes more than n digits. And there's certainly a way of making this thing from an n-digit description, which is to say just print the thing. And that's very fast. So the natural history of depth in a system like this is it increases gradually as long as there is statistical confidence that the current picture contains evidence for that history. But if you go so long the thing comes to equilibrium, then the current picture of it no longer contains persuasive evidence that that's how it got there. It could have gotten there many other ways equally plausible, including some ways generating it from a very verbose description quickly. And just as you said at the beginning, the description of its actual evolution has become verbose because the evolution went on for an exponential amount of time. So this is, I guess I just said the same thing here. The true history is no longer plausible because the number of steps in the true history has gotten too large. So as I said, oh, no, I hadn't said that yet. So this structure at equilibrium will still have complicated dynamics, and if we take 2 time slices that are not too far apart, they'll contain evidence of the evolution in between them, but the single time slice will be logically shallow. And the inhabitants of this world wouldn't, since they live in one time slice, wouldn't be able to see the complexity. Also, they'd be dead. So let's try to understand the role of this kind of complexity in our non-equilibrium world. And first of all, in an equilibrium world with short-range interactions, we get typically, except for some special things like being exactly on a phase transition or at 0 temperature or something like that, you get generically local correlations. That is, 2 sites may be more likely to be in the same state as in a different state. But if you go a long distance away, we get exponential decay of these correlations. And particularly if this site is correlated with that site, it's correlated through some intermediate system. So it's a state of the intermediate system. So this is just, I guess, what do we call this? An area law. So that's a typical behavior of equilibrium systems under generic fields at a finite temperature. However, in our non-equilibrium world, we have things that are very intensely correlated with things that are nowhere near them, never have been, and the correlations are not are not propagated by the intervening medium. So here are two coins with a picture of Elizabeth II on it, two different pictures of her, different shaped coins, and they were made in different places. And the main reason that they both have her on the coin doesn't have so much to do with her, but for a different person several hundred years earlier. So this cellular automaton is very much of a toy model, but I think that we can argue that fully quantum systems will behave similarly. They'll lose their complexity, their long-range correlations, and even their classical phenomenology as they approach thermal equilibrium. And this is the approach that was introduced by Zurich et al. Under the name quantum Darwinism, which I think is a bad name for it because I like it. It suggests reproduction and natural selection, and I think it should be called quantum spam. But I'm still working hard on getting the creator of the name, Wojciech Zurich, to consent to change it. So from now on, you will mostly hear it referred to as quantum Darwinism. Well, what is the idea? Well, some of you are probably familiar with this quantum Darwinism notion. I can give you a little review about it. It's one of the many species of decoherence theory. But I think I'll say that till the end. So the idea is here, if I let the Earth come to thermal equilibrium by just getting rid of the sun and letting it just live in its own recycled thermal radiation for a long time, I'm neglecting radioactivity and so on. Very slow things happening in the core and mantle. But so let the Earth come to thermal equilibrium by putting it in a reflective box. And then I think you can argue that the entire state inside the box would approach a microcanonical superposition of near degenerate eigenstates, and these are typically highly entangled, and they're free they have only short range correlation, and they're really even free of any kind of classical phenomenology. Now, so what?
What do you mean by classical phenomenology?
Well, that's one of these. The idea is that but classical phenomenology means that if several people look at the thing, they will see the same result, and so they can decide. They can say this thing has a. In the ordinary way of thinking, maybe by Bohr, you would say classical thing is macroscopic. It's a form of information that's not disturbed by looking at it. Mm-hmm. But the quantum Darwinist or spam way of looking at it says it doesn't matter how small a system is, if it's been observed enough times by different subsystems that don't interact with each other, then an additional subsystem of the environment looking at it sees the same thing as all the others did. Yes?
I might just be taking your diagram to too much at face value, but I was wondering, when you showed that image of the change, what about gravity? Wouldn't you still have a big lump in the middle of the mirrored box?
Oh yeah, you would still have a big lump, but it'd be like being inside a furnace that's all at the same temperature. You can't see anything.
Okay, but this would give some structure to everything.
Yes, but it wouldn't.
No, it wouldn't be very much.
In order to see that structure, you would have to displace it from its highly entangled state. You would have to observe it with some external light source, and you would have to displace it from thermal equilibrium. So what I would say classical phenomenology means a situation where there are some properties of a system that are replicated in many parts of the environment, and therefore that multiple observers can agree as to what these properties are. I'll say a little bit more about this at the end, because I think it's an interesting way of thinking about decoherence. But going on now, so in this picture we said that, well, this is random here. It really got there because of a long evolution. But maybe a structure that seems to have had the plausible evidence for it is that it got there by a long evolution. It could have gotten there in a less likely way as a random fluctuation. And this is the old idea of the Boltzmann brain. And the Boltzmann brain, for I don't know if there's anybody who hasn't heard of a Boltzmann brain, but the idea is that, and this was before the discovery of the expansion of the universe, one of Boltzmann's friends said, well, the big problem for statistical mechanics is to understand why the world has in such low entropy state. Why is it so far from equilibrium if everything tends to equilibrium? And this, I don't know what this person's name was. It wasn't Boltzmann. Boltzmann quoted him. He said, well, maybe the universe is infinite, and different parts of it are suffering from equilibrium fluctuations, as you would expect they would, and therefore you can find a part that has an arbitrarily large fluctuation from equilibrium. In fact, maybe even large enough to produce everything that we see. And that's the explanation of why our world is out of equilibrium. Well, later on, that idea got sharpened and made more ridiculous by saying, well, maybe the fluctuation isn't large enough to produce a whole universe with galaxies and planets and so on, but just big enough to make a momentarily conscious brain thinking that there's an outside world with galaxies and so on. And of course, it's embedded in this thermal maximal entropy background, which in a moment, like a couple of milliseconds, is going to fry this brain and it'll stop thinking anything. So that's what a Boltzmann brain is. And the Boltzmann brain has become a problem that is discussed by cosmologists, even this year. And I don't think that the inventors of the Higgs boson thought that the problem they were trying to solve was getting rid of Boltzmann brains. But that's one thing that it might be good for. So the point of this article here is that if our universe is, as it seems now, to be undergoing an indefinite expansion in which no matter how large it gets, it will still have a finite temperature. This gives a lot of place for these fluctuations to happen. So many of them that the number of fake Boltzmann brains is infinitely greater than the number of galaxies and ordinary brains. So the question is, why? We've got to do something to stop us from having this infinite future, because otherwise we would be atypically early in the evolution of the universe. So I'm getting now into the second idea of observer bias and trying to understand it. Well, another thing that made me think about this was last year when my 4-year-old granddaughter heard some people saying that the world was going to come to an end on December 21st because of the wraparound of the Mayan calendar. And I said, no, it's not. And she says, well, I knew it wasn't going to come to an end. And I thought, well, she's only 4, and her reason for thinking it wasn't going to come to an end was that she'd been around for 4 years, and it hadn't come to an end then, so why should it do it tomorrow? But this is actually not a very sound way of reasoning, because it could be that we're just lucky, and it has a half a chance of ending every hour. And so and I would say, how would it end? This is like a suggestion of an asteroid impact, but the most dramatic way for the world to end is a vacuum phase transition, similar to what ended the cosmic inflation, and that would, to a still more stable vacuum, that would propagate through all of us at the speed of light. So it would be like dying in our sleep. We wouldn't know what happened to us at all. The world would just end. And so all of the talks that are scheduled for later in this week wouldn't happen. So this idea is part of what's called a doomsday argument. And the idea is to say, well, we shouldn't be that's the first idea about the Donald Duck. We shouldn't be at an atypical place in space or atypical place in time if we take into account places that we know we can't be because they're empty space, or times that can't be, or parts of the multiverse where the laws of nature are so different that there could be no organized structures. So the hazards of thinking about this is, well, you see why it's the doomsday argument, because a lot of people, including myself, like to think that with good management, human civilization could go on for billions of years and have lots of people having, most of the great works of art and so on have not been composed yet. And so Carlton Cave says, well, let's imagine you try to think this way and you go into a birthday party and say, how old is the birthday person? And they're 50. Well, then there's half a chance they'll live to be 100 and a third of a chance to 150, which is, I guess that would be a joke in a birthday party. Actually, I told this joke at John Prescoll's birthday party, but with 60. And he thought it was funny. But if you go into a maternity ward in a hospital and say, and pick up this newborn baby or something that's a couple hours old, and you say, oh, well, it probably won't live to be a month old, you probably get some, maybe you would even get some wounds. Anyway, so the thing that's been neglected here is that there's sometimes other evidence as to that will invalidate the assumption of typicality. Now, by contrast, a very disciplined way of thinking about typicality was used at the end of the Second World War, where they were planning the Normandy invasion, and they wanted to know how many tanks the Germans had. And they had some reports from spies, but the reports from the spies were not very consistent with each other, and there was a lot of disparity among them. So another approach was to keep a track of the serial numbers of some of the tanks, probably on the order of dozens of them, that had been captured in battle, and use that to estimate how many tanks have been manufactured. So that gives a rather poor estimate if there's only one tank captured. And it gets to be a very good estimate, good enough for planning invasions, when it's a reasonably small number of tanks. And it turned out to be quite accurate as to how many there actually were. Now, don't try that with any modern army, because the tanks now are numbered, or any other kind of military equipment, either randomly or using a supposedly cryptographically strong pseudo-random number generator. So you can't figure out which order thing was made in by looking at its serial number. But they hadn't thought about that back in. They should have, but I guess it was sort of the Prussian philosophy going on beyond its usefulness. Well, now a very recent kind of apocalypse, it's a kind of a private apocalypse, is the black hole. Yeah.
You described the apocalypse a little bit, in sort of like tomorrow. But of course, I mean, we have a lot of evidence that, it would at least take some time, right? Somewhere in the universe, something would happen. It would take.
Thank you, Barbara, for bringing that up, because
energy, it would take quite a bit of time before it would affect us.
Yeah, well, I'm grateful to you for you bringing it up, because if you're worrying about that, you ought to bring it up quickly, before the universe ends. Now, in case anybody else is worrying about that, there is an argument, I think a sound argument, that I'm going to mention on the very next slide, if I get to it, which explains why we shouldn't worry about a vacuum phase transition in the next billion years. So,
based on some knowledge,
based on some other knowledge of things,
we have now,
yes, and based on things that are not undermined by the fact that if it had happened, we wouldn't see it. So that it's a very important, maybe the most important thing. But I just wanted to mention this thing because it's such a fashionable topic, the black hole firewall. So the idea is that if you have a young black hole, you can fall in through the horizon and you get destroyed eventually. Whereas if you have an old black hole, as soon as you hit the horizon, you get vaporized and you can't tell anybody about it. So it's a really private kind of experience or lack of experience. It's just like the same question where I was asking about the whole universe, except it's only for one observer. So if there are no firewalls, Alice can learn about it. Like she would, even after the black hole became old, she would go in like that, but she couldn't tell anyone. So it's like the tank problem with not even a whole tank. And so my idea about this, which is an area which I know almost nothing about, as Jeff Grinstein, my IBM colleague, Jeff Grinstein used to say, I know enough about it, only enough about it to be dangerous to myself and others. So could it mean that because of this experience is so private and so uncommunicable that the presence or absence of a firewall is even ontologically a sort of a nearly moot question, like the question of which path a particle followed in the two-slit experiment? And that perhaps it's not such a problem for the same reason that a simpler version of understanding black holes was considered not too much of a problem until this firewall business by the theory of black hole complementarity. Well, I hope I'll get somebody who understands black holes to tell me whether that's a stupid idea or not. Well, getting back to your question, Barbara, Max Tegmark and Nick Bostrom, does anybody know Bostrom? He's at Oxford, I believe. Argue that any kind of galaxy-destroying apocalypses are not very likely for a billion years. And the reason is that we have evidence about the potentially habitable planets were being formed for quite a long time before the Earth was formed. And I bet when I say potentially habitable, I mean they are old enough to have been formed from second-generation stars and have heavy elements in them, not just hydrogen and helium, and that they're the right distance from a star of the right brightness, that it could be an Earth-like planet there. And you say, well, this is an astrophysical, astronomical observation. This is the apparent distribution of times when such things, well, it only goes up to here because this is the present. Oh, no, this is the present time now, yeah. Well, no, it goes up to about this far. Time since the Big Bang, we go out to about this far. So what it says is that planets were being formed for quite a number of billions of years, on the order of like 7 or 8 billion years, before the Earth was formed. Now, if there was a chance of 1 in E of the whole universe disappearing every billion years, then the age distribution of planets that got formed before this bad thing happened would be squeezed over to the left side. Or to put it another way, how likely, given that the Earth had to be formed, how likely was it that it was formed so late? And if the annihilation time scale was only 1 billion years, then there was only one chance in 1,000 that the Earth would have been formed so late, because it would have had to escape like around 20 chances for it to have been annihilated by a vacuum phase transition. So that's why you shouldn't worry about it. And so when you put that together with the paper I showed you earlier, Buddy and Carroll, which says that because of this problem of Boltzmann brains in the late universe, the Higgs boson or something else ought to make the world disappear on the time scale of order of a few billion years, because otherwise we get this bad problem. So this says the universe is about likely to last about as long as it has already, which is a nice result from people who like typicality. However, a more severe doomsday question occurs with civilization, which seems to have existed for only about a millionth of the time potentially available for it. So let's look at some typicality or mediocrity and atypicality in Earth's history. So, roughly speaking, the Earth got cool enough for life to exist around 4 billion years ago. and it's going to get too hot for life to exist in another couple of billion years. And here's where we are now. And simple life got started right at the beginning, within a few 100 million years of the beginning. So that's kind of evidence that it's pretty easy to happen, and it'll happen on most Earth-like planets. Not super strong evidence, but it's fairly strong evidence. Complex life, we had to wait sort of on half the expected time till the end for that to have happened. Things that leave multicellular organisms. And of course, civilization is just a tiny little thing, about 10,000 years or so. And so it seems that simple life is likely. Complicated life seems to be relatively unlikely. And so it maybe in most worlds it never happens at all, but we're a lucky one because we have to have it in order to be here ourselves. And civilization is severely non-mediocre. The problem is not that it arrived so late, but that, well, I guess you could say the problem isn't with the past. It looks like it's something that's fairly unlikely, but why are we so close to the beginning of the time that it should exist? And that's a little worrisome. And that's a bigger worry than the vacuum phase transitions. So why is civilization so atypically new? And well, as I said, vacuum phase transitions are not the explanation because they don't happen often enough to squeeze us into such extreme newness. So maybe civilizations are unstable and don't last more than a few thousand years. And of course, I'm sort of a technological optimist. And it seems to me we ought to be able to protect ourselves by learning how to be peaceful and cooperative. Or if we can't do that, at least by colonizing space so that it's hard to wipe everybody out. And besides, if there were civilizations that got wiped out, then why don't we see the remains of previous ones? Well, maybe they're kind of rare, maybe less than one per galaxy, which would also explain why we haven't run into any extraterrestrials yet. But there's another, I would say this is a very slender hope, but it's something that some people at least hope for, and that is the idea of perpetual newness. Maybe a billion years from now, there will be still people, or our cultural descendants, but they will not be worrying about or thinking about the fact that civilization has been around for a billion years. They'll be thinking about some new thing that's happening right then, and they'll say, it's upsetting that this new thing that we like so much, maybe some new kind of mobile phone or something, has only been around for a short time. Is that a reason for thinking that life as we know it is about to disappear? Now, it's not only, and I would say that I think David Deutsch's book on the beginning of infinity takes the mathematical fact that in infinite sequence of, let's say, the sequence of natural numbers, all of them are atypically small. Everything is too close to the beginning. And so maybe what's our future is like that. It's a very optimistic thing. But also dictators like to think of themselves as being very near the beginning of a long future era. And this is a building, as are many buildings of this sort in Italy, which says that it was built in the 7th year of the fascist era, which would have been 1929. Now, of course, back then, 1929, it was probably before the stock market collapse, and the fascists were feeling pretty self-confident. Just a couple weeks ago, Andres and I were, and then some of the rest of you, were in the conference in Erice in Italy. And part of that building is a cornerstone, which gives the date, both in conventional years, 1937, and it also says XV. And I looked at that XV, I said, there's something about that XV. It is the 15th year of the fascist era. And they were not feeling quite so confident then. So they put it in both formats. So also hippies. I was a hippie at one time, around 1967, and one of the inspirational slogans we had is, "Today is the first day of the rest of your life." So I don't know where this idea goes to. It actually didn't come from a very good place. And it's not, to me, very persuasive as a reason why we should expect a long and infinite future. But let me say, why do we believe that we are not Boltzmann brains? Actually, forget that question. Why do I believe that I'm not a Boltzmann brain? Because if I were, I wouldn't think the rest of you were real. Because even more probable than your traditional Boltzmann brain is something you could call a minimal brain that's just barely able to ponder its own existence, but it doesn't have false memories or perception of an outside world. So I'm more than a minimal brain, so not only do I exist, but also the whole surrounding universe. But what would a minimal brain think? Would it even think about cosmology? And I think it's
What is a minimal brain?
a minimal brain is something that's like a Boltzmann brain. It's a fluctuation, but it's just barely able to think. It doesn't think that there are other people. It doesn't think that there's stars in a three-dimensional world. Well, I might think of a three-dimensional world. The Boltzmann brain idea was that our world might be a fluctuation. But you say, well, what's the smallest fluctuation that could think? Well, that's a problem where you have to even struggle to say what you mean. It's very hard, as I say, to put yourself in the shoes of a minimal brain. And yet, if you can't say...
In this lecture, you are not a minimal brain. This is the anthropic principle.
What?
Because you are giving this lecture, you are not a minimal brain.
That's right, and that's why we
The point is also, we are not just
There would be
separate.
no lecture if you are a minimal brain.
yeah, I know I'm not, and what I'm saying is, not only because I'm aware, I'm thinking in a way that a minimal brain wouldn't think. I don't think I'm a minimal brain, and therefore I don't think I'm a Boltzmann brain.
I'm not sure it's about you. I mean, it's about civilization,
Well,
right?
excuse me, you
say,
think it's
I
about
can
you,
think
right?
about- No, you say you can think about, the universe and so on.
Yeah.
But that's not at all true. I just rely on observations that I've heard about from other people, just knowledge that human
Right,
mankind
it's
has.
so different.
I'm not a very clever brain in that
Yeah.
aspect. I could be telling a child the same information. We do not understand at all. I mean, I'm not sure that I, as a brain, or because you say the I, but you probably mean the knowledge assembled and the concept assembled by mankind through observations.
Exactly, and we, both our individual experiences are much more complicated than a just barely conscious one, and certainly our social experiences and having science that we consider true and
They're
explain.
not so different from animals. I mean,
No, but these animals, I think that-
if it's about our direct, I don't think that we're so different from those
No.
bacteria at some
Animals
point.
have that
Really,
minimal
I think
brain.
it's more of a.
Well, this is clearly a question I don't know the answer to. But now here's something I really know. See, I'm not sure I don't. I'm pretty sure I don't understand. But this is something I really don't understand, and maybe some people do understand. Ever heard of the Sleeping Beauty problem or the absent-minded driver problem?
Yep.
Well, the absent-minded driver problem I think came a little first, and it was the idea of somebody who's trying to drive home on a road that has two exits, and they both look the same, and the person is very absent-minded, so they don't remember whether they passed the first exit, and they have to decide how to get off the road. They live at the second exit, unfortunately, and if they take the first exit, they end up in a very bad part of town and get a payoff of 0. If they skip the second exit, if they go to the second exit and get off there, that's their home, and they get a payoff of 4. But if they miss that, then the road goes on for a long time, and they have to get off and sleep in a motel, which is a payoff of 1. So the optimal strategy for this person is a probabilistic strategy where they toss a coin with a certain bias, and they have some danger of getting off at the first exit, but at least a reasonable chance of getting off at the second exit. But now the Sleeping Beauty problem is probably safer than being being that sleepy and trying to drive. Sleeping Beauty goes to sleep on Sunday, and then on Monday they wake her up and talk to her a little bit, and then give her an amnesia-inducing drug and let her go back to sleep. Then they toss a fair coin, and if it comes up heads, they don't do anything. But if it comes up tails, they wake her up again on Tuesday, and then again give her the drug and put her back to sleep. And on Wednesday, the experiment's over. They wake her up. She goes home. But the question is, when she is awakened, which is either Monday or Tuesday or both, or it could be Monday. It certainly is going to be Monday. It also happens Tuesday. What is her guess as to outcome of the coin toss? And apparently, there are camps that believe that it is 1/3 heads, and there are other people who believe that it's 2/3, and both of them give rise to rather uncomfortable consequences if you try to use them in anthropic reasoning about worlds, multiverses that have different numbers of observers in different worlds. Now, I'm barely able to suggest what these problems are. Well, you can give some argument as to why it should be 1/2, and another argument as to why it should be 1/3. Well, there's 3 situations. She could be awaking on Monday, which happens with probability 1/2. She could wake up on Tuesday with probability 1/2. And if it's on Tuesday, the coin toss is certainly tails, because they wouldn't wake her up unless it was tails. Well, anyway, so there's Bostrom has got an article which I haven't understood yet, which he alleges is a proper solution to this problem that you need to understand before you can think about anthropic reasoning. So, and I say that cosmologists do worry about this a lot, and here are some other papers about that. But cosmological models resemble the rest of science, because they're based in part on observation as well as theory. And the reason that we believe in cosmic inflation, or the reason it's an appealing theory, is that it agrees with observations about accelerating expansion of the universe and uniformity of the cosmic background and so on. So, but if you're trying to think about the set of all possible universes in a purely mathematical way, is there a way to do that without having any contamination from physics? Now, I think a physicist would say that anybody who has that kind of idea shouldn't be a physicist. But maybe it's an idea we should think. You might say, well, what are all the kinds of universes that could exist don't distract me with any evidence from our actual universe, because that's the a priori probability that we ought to sample from and then throw away the parts that are anthropically impossible. Now, this approach was suggested by Schmidhuber in the millennium year, using essentially the monkey graph as saying, well, what if this graph is the set of outputs of a randomly programmed universal computer is the set of possible universes, which we now should prune down by some kind of observer-basis selection principle. You might say, before you want to go that far, what about including some sort of universal physical principles like reversibility or locality or superposition? And a paper that went into that kind of approach somewhat is a paper by Lloyd and Dreyer, which invoked the universal computer in generating a universal path integral. So having made these decisions in one way or another and banished biology and most of physics from our theory of the possible universes, we're still left with the problem of defining an observer. And as I said, what could be the criterion of observership? Well, back in that monkey graph, I pointed out that some fraction of the nodes in it were self-simulation nodes. And if you just say a possible universe is a node on the monkey graph, and that node is conscious if it itself is capable of universal computation. And then we get a kind of a reassuring positive answer. Yes, the universe, the multiverse, gives a finite probability for generating complexity. That is, this graph of all possible computations has a finite fraction of subgraphs that are, or subtrees that are similar to itself. Well, that's kind of trivial and probably not even worth saying. So another way of approaching it is suggested by Murray Gell-Mann's concept of an IGUS, information gathering and utilizing system. So you would say, go and take this collection of all possible structures, which are given by some purely mathematical prior, and see if you can find ones that contain parts that make maps or representations of the whole thing. That's an idea that can be defined somewhat by information theory. And say those are the ones that have, I wouldn't necessarily call it consciousness, but some attempt to understand and deal with their environment in the way that living things often do, not just people. And for the reasons that you might say that those are the scientific universes, the universes in which there is something that tries to make an accurate model of the whole embedded in itself. And by that very redundancy between the model and the thing that it models, we have the fact that such universes must be displaced from thermal equilibrium because they have that entropy deficit. And that is about all I want to say. I've got some references if you want to look at them. But this is a good time to stop, I guess, and take some more questions. If there's anybody who wants to know about quantum Darwinism, I've got a few extra slides about that and a few other things. Okay, but let's just stop here and stop this distraction stuff. Okay, that's a good place to stop. Today is the first day of the rest of my life. So, any questions?
May I ask you about this analogy with the Sleeping Beauty program? Because I think I missed the point of your example. Because in my view, this controversy has been going on for a decade almost.
Yeah.
In my view, it originates from the confusion about the questions we asked the observer, and then I think it actually stems from what you said, because you said, "What's the chance that I will be woken up on Monday?" And the chance is 1. That's the probability. It's the ignorance of the observers which generates this sort of.
No, you ask the observer not whether it's Monday or not. You ask them whether the coin turned up heads or tails.
Yeah.
Yeah.
But
and there are versions of it where you tell them that it's Monday. Yeah, I think suppose you tell them. I think maybe I don't know if that was part of the setup of the problem. You tell them that it's Monday, and then you ask them, how do they think the coin? I'm not sure I've got the problem right. As I said, this is a problem I barely understand. Yeah.
Very good, very interesting talk about this. And one suggestion I had for maybe a sort of what I think is an equivalent problem. In Barry's talk, he mentioned some principles that people have offered to do with time having a role in how.
Yeah, the time is sort of irrelevant. Yeah,
very confusing.
Yeah,
issue. And I thought a nice way of reframing it is that you have a person who heads. The person is, you're put to sleep. They're left alone. There's just one of them. Tails. you
make two
you
of them.
clone them and you put them
Yeah.
in separate rooms.
That's the thing. That's the version that has to do with possible universes, and some of the crudest applications of the doomsday principle talk about humans as if they were totally independent entities. In fact, we're part of a civilization. We communicate with each other. And so, as Barbara maybe suggested, it's better to regard us as a single individual rather than as a bunch of individuals. But in these models, that sort of time-independent version of the Sleeping Beauty problem is to say, they toss a coin, and if it's heads, they create one observer. And if it's tails, they create two observers who can't communicate with each other.
Yeah, yeah.
And then you ask, what's the right, and these observers don't know whether they are, whether they're one of the one observer, the only one there is, or whether they're one of two. And so you have to decide, and that kind of problem, of course, comes up in these multiverses where they're non-communicating parts of the universe, and there might be civilizations in all of them. And how do you weight these things? So that's actually a better way of thinking about it.
In this entire setup that you had with like cellular automata or the monkeys typing and whatever, so you always have an algorithm generating our universe, which implies that there are only like countably many different universes. Is that an issue at all? Because we don't have any evidence that our universe has a finite resolution. Or
Well, that's a problem that comes up a lot in cosmology, because in these infinite universes it becomes hard to assign relative probabilities to different things. However, some of the approaches might be to say, at any one instant, like from here, only a finite portion of the universe is accessible. And it's also only accessible in finite precision because of, let's say, energy, time, or even, let's just say, the holographic principle. Okay. And therefore, you can make you can identify the distinct possible universes as with the countable set. Or you could say it's they're superpositions living in a Hilbert space of countable number of dimensions.
okay, so you just assume that it's the case.
Yeah.
Okay. But say if that was not the case, so if it was a continuum, like over countable set or something like that,
Yeah.
could you draw the same conclusions?
Could you
draw the same conclusions about like our why is it that we exist so early in the universe and stuff like that? Could you draw the same conclusions even though?
Well, that argument of Tegmark and Bostrom really was it wasn't drawing entirely from a mathematical view. It sort of gave the existence of a universe that's sort of like ours, but might be annihilated. So they took as a legitimate input data the distribution of times when planets had formed in the galaxy.
Okay.
And so that's kind of thinking of it in, you might say it's thinking of it as in continuous time and space, or you could say that since it was dealing with a finite volume of our own universe with a bound on its energy, that it was approximable to by a discrete system of a limited dimension, although very high dimensional one. And they were just making an argument that really didn't depend on whether the variable was continuous or discrete, as long as it had enough values.
Well, if there are no more questions, then let's end the session, if not the word.